In the operation of a ship's power plant, steam must be used over and over again to conserve supplies of fresh water and fuel and thus increase cruising range. The endless process of turning water into steam, putting it to work, and turning it back into water is known as the steam cycle. It is a complicated and highly efficient system that has evolved over the years from the early days of man's use of steam. This rudimentary power plant, consisting of a simple boiler and an engine, had many disadvantages. It used a lot of fuel to produce steam of low pressure and temperature. The steam was lost after being used. This wasted fresh water and fuel, a serious matter where these supplies were limited. Periodically, the plant had to be shut down while the boiler was refilled. By connecting a large tank to the exhaust, much of the steam could be condensed for further use. Condensation was aided by adding a reservoir tank into which the hot water drained. Moreover, the hot water could be dipped from the reservoir tank and carried back to the boiler to go through the cycle again. This arrangement, then, involved 4 phases: generation of the steam, expansion to turn its heat energy into useful work, condensation of the steam back into water, and feeding of the water back to the boiler. Let's see how these phases have been developed in the efficient power plant of a modern vessel. In contrast to the primitive boiler, today's naval boiler is designed to get as much as possible of the heat energy out of the fuel and to produce steam of high pressure and temperature. Generation may be shown in this simplified boiler. The hot feed water enters a drum and fills several thousand feet of tubes. Underneath is the furnace with several burners. The burners mix air and oil in the right combination for complete combustion to produce maximum heat energy. The hot gases of combustion rise between tubes, which are arranged so that as much of the heat as possible is transferred to the water. Steam and hot water rise through the tubes, return to the drum, and are replaced by water from the drum, establishing a natural circulation of hot water and steam through tubes and drum. A boiler having only these simple provisions for converting water to steam produces what is known as saturated steam. This laboratory model shows saturated steam being produced. Saturated steam will have the same temperature as the boiling water, in this case 212 degrees Fahrenheit. No amount of heat can raise the temperature of the steam higher than that of the water with which it is in contact. However, if tubes are located away from the water, the saturated steam flowing through them can be heated to a much higher temperature. In this case, the steam has been raised to 312 degrees Fahrenheit. The process of adding heat to saturated steam is called superheating. In the boiler, the saturated steam is led away from the drum into a group of tubes called the superheater, which is located in a zone of high gas temperatures. Of course, this is a very simple type. Modern naval boilers are more complex, but all are based on the same principles of steam generation and superheating. The next phase, as we saw in the early steam cycle, is the expansion of steam in the engine to produce work. This engine, typical of those in modern naval vessels, is divided into 2 or 3 turbines, which turn the propeller shaft through reduction gears. As explained in the film, How Turbines Work, the rotors are set in motion by jets of steam. These steam jets are created wherever the steam passes through a nozzle or nozzle-like plating from a region of high pressure to one of lower pressure. Each drop in pressure may be compared to a drop in altitude, as in the case of a river pouring over a dam. Each drop produces the velocity to turn a wheel or wheels. Eventually, we reach zero pressure, or sea level. If we could lower sea level, we could put in another dam at the mouth of the river, and thus get more work out of the river. In the next phase of the steam cycle, we can do this very thing with steam by reducing its pressure below the pressure of the atmosphere. This final reduction in steam pressure is an important function of the condensation system. It is the condensation of the steam in the main condenser which causes this reduction to below that of atmospheric pressure and makes available extra energy to turn the turbine rotors. A laboratory experiment shows what happens in the condenser. The glass flask and its covering are filled with steam and sealed so that air cannot enter. Then the flask and its contents are cooled. This cooling condenses the steam, and something else happens. Condensation reduces pressure below atmospheric, as proved by the fact that the pressure outside pushes the covering into the flask. In the ship's main condenser, the steam is cooled by seawater, which is forced through small tubes. Here we're looking down into the compartment where the steam passes from the turbine exhaust to come in contact with the cool tubes below. Through this opening, the seawater enters the supply header and feeds into the battery of cooling tubes, which we have just seen from a different point of view. The seawater emerges into an overboard header on the other side of the shell, without having had direct contact with the steam. In a condenser, designed for use on destroyers, there are no less than 20 miles of tubes. As the exhaust steam passes into the condenser, it condenses into drops of water through contact with the cooling tubes. The water, now known as the condensate, collects in the hot well. It is removed from the hot well by the main condensate pump. Air as well as condensate must be pumped out of the main condenser, because air cannot be condensed like steam to form a vacuum. Air is removed from the condenser by a steam jet pump called an air ejector. Steam from the auxiliary line is fed through a nozzle, which causes a loss in pressure and a consequent gain in velocity. The steam jet carries along the surrounding air, establishing a vacuum which draws air out of the condenser. The mixed air and steam pass through the air ejector condenser, where the steam is condensed into water and the air is discharged to the atmosphere. Condensation is caused by passing the steam between cooling tubes, as in the main condenser. But here, the cooling tubes are filled not with seawater, but with the condensate, while on its way back to the boiler. Therefore, the air ejector steam jet not only removes air from the main condenser, but also gives up heat to the condensate. These, then, are the units of the modern condensation system: the main condenser, the condensate pump, and the air ejector. As we saw in the early steam cycle, the final phase is the feed system. In the modern naval feed system, the deaerating feed tank does a big part of the job. For one thing, the deaerating feed tank acts as a reservoir to supply feed water to the boilers under all conditions. Another highly important function of the deaerating unit is to remove any air still remaining in the water. At high temperatures, air corrodes boiler tubes like acid. As the water passes through nozzles, it is broken into fine spray. In this way, air is released from the water and exhausted from the tank. The falling spray collects in a cone-shaped device and spills out through a narrow opening. Meanwhile, steam from the auxiliary exhaust line rushes into the same narrow opening and mixes with the water, heating it on its way back to the boiler. Pressure and temperature are raised step by step through feed and generation, just as they are lowered step by step through expansion and condensation. Two pumps, the main feed booster pump and the main feed pump, both working on the centrifugal principle, are used to push up the pressure in stages from the low pressure level in the feed tank to the high pressure level in the boiler. Another unit is the economizer, which further heats the water before it enters the steam drum. The economizer is located in the boiler, where it absorbs heat from the gases before they pass up the stack. The water entering the drum is ready for another trip around the steam cycle. The boiler also supplies steam for the auxiliary turbines and generates steam for the turbines which drive the boiler's air blowers and fuel supply pumps, supplies steam for the main condensate pump turbine, and steam for the turbines which operate the main feed booster pump and the main feed pump and other auxiliary turbines. The exhaust steam from these turbines goes to the deaerating feed tank. Here, as we have seen, it is used to remove air and to heat the feed water. The units in the steam cycle make a complicated pattern, but fundamentally the cycle is a simple one. The boiler produces high-pressure superheated steam. The steam is expanded in the turbines and turned into work. The condensation system condenses the steam, creating a vacuum, which makes more energy available to the turbines. Finally, the feed system removes air from the condensate, increases its heat, and delivers it to the boiler. Altogether, the units of these systems provide a continuous flow of steam and water, converting water into steam and steam back into water in a continuous and efficient cycle, thus meeting the all-important requirements of conserving fuel and fresh water and increasing the ship's cruising range.